Firstly, I would like to thank the organizers for this opportunity. So I'll be talking about some work that was done in collaboration with Samriddhi and Saptashi, both of whom are from ICTS. So I'll begin with an important problem in quantum information science, and that is the problem of benchmarking quantum devices. So when you run your quantum algorithms on your quantum computers or your quantum devices, you start with this initial product state and you apply quantum operations, which are basically unitary gates. And eventually, your system is in this state with this intricate web of entanglement, such that local patches of your system look to be in this featureless steady states, which are your infinite temperature states. And this is what occurs when your quantum device works well. But suppose your quantum device is got a lot of errors and it's got these unfavorable couplings to your environment or some lossy channels, then your system is globally at an infinite temperature state. And the takeaway lesson from this caricature is that local observables relax to the infinite temperature values in both settings, the setting of scrambling in the right and decoherence in the left. And as a result, to benchmark whether your devices are working properly, you require global observables to distinguish between scrambling and decoherence. And Project Ensembles, which is what I'll be talking about in my talk, was introduced as an attempt for benchmarking quantum devices. And the motivation is that in modern day experimental platforms like trapped ions, superconducting qubits, and so on, high fidelity measurements of many degrees of freedom are feasible. And the schematic is as follows. You have some trivial state upon which you have some unitary evolution. It could be a Hamiltonian dynamics, or it could be dynamics affected by a random unitary circuit. And you make measurements on your system, on all parts of your system, save for a local subsystem, which I label A. So you make measurements on subsystem B. And by doing so, you generate an ensemble of states on A condition on measurement outcomes in B. And this is what you define as the predicate ensemble of states, which is just a probability distribution in the Hilbert space. And this predicate ensemble, and there's been a lot of work that has discussed this, is observed to cover the entire accessible Hilbert space as uniformly as possible. So in more concrete terms, what this means is that your predicted ensemble is basically a discrete sampling of your Haar ensemble or your Haar measure. And this was introduced, predicted ensembles were introduced in this experiment in 2023. And for interest of time, I'll just skip the details of the experiment. And I'll be happy to take questions on this experiment later. But the takeaway from this is that when you have just scrambling phenomena, so just pure unitary evolution in your system, your predicted ensemble just converges to this Haar ensemble as described by the probability distribution that you see in your top right. And when you have decoherence in the system, each instance of your predicted ensemble converges to a maximally mixed state. So that's why your probability distributions peak into this particular value, close to 0.5. So motivated by this experiment, you can draw this very simple caricature of predicted ensembles. At one limit of zero information loss, you have the predicted ensemble being your Haar ensemble, and at the other limit, each instance of your predicted ensemble is a maximally mixed state. And so our question has to do with probing quantum information scrambling in settings with information loss. And the way we model information loss is in its simplest form by considering measurements which are lossy. So you have the cartoon I drew earlier. You now just trace out a certain subset of your measured sites, and you discard them. And you get what you call a partial predicate ensemble, which is introduced in these two papers by you and Mandel et al. In just past few months. And each instance of your partial predicate ensemble is just a partial trace of your discarded sites of each state in the predicate ensemble. And for generic unitary dynamics, it's been shown that these partial predicate ensembles are described by these generalized Hilbert-Schmidt ensembles, which are just your partial traces of your Haar ensemble, and this is quite unsurprising. So what we anticipate is that as we tune the amount of information that's lost, as we tune the parameter of the number of traced out sites, the discarded measured sites, we anticipate a crossover from a Haar ensemble to what we call a trivial ensemble, where each instance in the predicate ensemble, partial predicate ensemble, is a maximally mixed state. And so we first begin with a model with which you just have a random unitary acting on your system. So this has got no dynamics, nothing. And to diagnose the triviality of your partial projected ensemble, we use the relative entropy between the average state of the projected ensemble and each state, projected state in the PPE. And yeah, so we have a couple of results for your random unitary U model, where we first establish that, so these are the theorems, but informally what these theorems mean is that you have these theorems establish when your partial projected ensemble approximates the generalized Hilbert-Schmidt ensemble. And the second theorem establishes when generalized Hilbert-Schmidt ensembles look like your trivial ensemble. And this result comes from just the key ingredient in this result is this probability distribution of your eigenvalues of your post-measured states. So since your relative entropy, which I introduced on the left, is a spectral function of your states, that probability distribution is enough to compute what the relative entropy looks like in different regimes. So the key takeaway from this last slide was that when your subsystem A is smaller than the number of sites that have been traced out, B what's parameter labeled as B loss, your relative entropy scales exponentially, it exponentially decays with system size. And if your subsystem A is larger than the number of sites which have been lost, then it scales as a volume law. And what this means is that your PPE looks like a trivial ensemble in one regime and looks like a broadly distributed ensemble in another regime. And this is for a model without any dynamics, but a similar behavior can be seen for PPEs in locally interacting models at late times. So what we see is that when you plot your relative entropy as a function of time, at late times it shows similar scaling to the results we got in the random unitary model without any locality. So all that is good, but when we ask these questions, often we have to also understand, you're asking what is the effect of measurements on one subsystem on another subsystem, and what kind of ensembles of states are generated as a result. And this question would be incomplete without asking what is the nature of an entanglement between those two subsystems. So we are studying ensembles of states generated by measurements on B retained on A. So now we ask what is the nature of the entanglement between them for the models that we studied. And this is a question that was asked in this recent paper in 2021, where they studied the entanglement phases of these random pure states in tripartite systems. So you have a random state, a pure state, and then you tripartition it, and one part is traced out, and you ask what is the entanglement between the remaining two subsystems. And yeah, so this information phase diagram that you obtain, I'll just take 2 more minutes, is you have, so the entanglement phases described in that paper was you have the subsystem A and B retained, which are disentangled okay, so I'm parameterizing the subsystems by gamma and P, and I'm drawing a phase diagram where these P and gamma are a parameter space. And when your P and gamma are quite small, your subsystems A and B are completely disentangled. And when they are large enough, they're entangled. And these entanglement phases can be explained by simple monogamy arguments, where so these states are as entangled as they physically can be. But so that's what explains the maximally entangled phases. But when you have 3 subsystems and 2 of them are maximally entangled, those subsystems cannot be entangled with any other subsystem. And that's why that leads to a decoupled phase, which is this gray area. And what's interesting about the result we just discussed is that these phases in which the relative entropy was vanishing and was scaling as a volume law, they do not respect the boundaries of this entanglement phase. They cut right through. So this light green region is what we call the measurement invisible phase, where the relative entropy scaled as exponentially with decreasing system size, and it's basically you got a trivial ensemble. And the blue region is the measurement visible quantum correlated phase, where your relative entropy scale as a volume law. So this green phase is quite interesting, and it's a new information phase defined for tripartite systems, and it has no analog for bipartite systems. And why this phase emerged, I'll just quickly end with the last slide. So, as I described earlier, that monogamy can explain the various entanglement phases of this tripartite random states, but monogamy arguments are not applicable to describe this measurement invisible regime. So what argument actually does explain it is statistical argument similar to page and canonical typicality, where when you have a state which is uniformly
Sorry,
sampled
Allan,
from the
we should
space,
stop.
yeah, I'll just, yeah. Up to half the system qubits are in a maximum state. So this is a result that typically holds. So yeah, so